All right, let's get right into it. If you're studying to be a chemical technician or engineer, we're going to talk about one of the most powerful tools you will ever use in your entire career. And no, it's not some fancy piece of equipment or a complex computer program. It's just a single, elegant number that gives you almost total control over the fluids you work with every single day.
I want you to picture this for a second. You're running a massive chemical reactor. Inside, there's a reaction kicking off a ton of heat. Now, is everything inside going to mix perfectly, spreading that heat out nice and even for a safe, efficient process? Or are you going to get dangerous hot spots that could lead to a thermal runaway, maybe even an explosion? Look, the difference between those two scenarios, it's not luck. It all comes down to understanding how your fluid is flowing.
And here is the wild part. We can actually predict and control these incredibly high-stakes outcomes with just one number. It is literally the key that unlocks the secrets of how any fluid is going to behave, whether it's water flowing through a pipe or even blood moving through an artery.
So what is this magic number? It's called the Reynolds number, or just Ray for short. Now, the official definition, it sounds a little dry. The dimensionless ratio of a fluid's inertial forces to its viscous forces. Okay, but what on earth does that actually mean? Well, when you boil it all down, it's really just about a constant battle that's happening inside every single moving fluid.
So think of it like this. You've got two opposing forces. On one side, you have inertial forces. Let's just call them the bully. This is the fluid's momentum, its tendency to just barrel forward and stir up chaos, creating all these messy swirls and eddies. But on the other side, you have the viscous forces. We'll call them the peacemaker. This is the fluid's own internal friction, its stickiness, that's always trying to calm things down and keep the flow smooth and orderly. And all the Reynolds number does, it just gives us a score. It tells us who's winning that fight. And you know, there's a super easy way to remember this. You don't even need to have the full equation memorized right away. Just keep this little phrase in your head. Fast and dense on top, slow and sticky on the bottom. The stuff that helps the bully, you know, how fast and dense the fluid is, that all goes on top in the equation. And the thing that helps the peacemaker, that stickiness, the viscosity, that goes on the bottom. So, simple math, right? The bigger the number on top gets, and the smaller the number on the bottom gets, the more chaos you're going to have.
This whole idea, it's not new. It came from this guy, Osborne Reynolds, way back in 1883. He did this really elegant, simple experiment where he shot a thin stream of dye into water that was flowing through a glass pipe. At low speeds, he saw a perfect, straight, clean line of dye. But as he cranked up the velocity, boom, that perfect line just erupts into these beautiful, chaotic swirls. He literally made the invisible visible.
Okay, so here's the really important takeaway from all this. The value of the Reynolds number doesn't just tell us who's winning the fight. It tells us exactly what the flow is going to look like. That number lets us classify flow into three totally different, totally predictable types. We call them regimes. So let's break it down. For flow inside a regular pipe, we have these handy thresholds. If your Reynolds number is less than about 2100, you've got what we call laminar flow. It's beautiful, it's orderly. Think of it like cars all staying perfectly in their own lanes on a highway. Now, if you push that number above 4000, everything changes. You get turbulent flow. It's chaotic, it's messy, but it's amazing for mixing, and that bit in the middle, that's the transitional zone. It's unstable, unpredictable, and honestly, it's a place engineers just try to avoid.
Right, so let's lock in on that first one. Below 2100, here, the peacemaker, that internal stickiness is completely in charge. Any little disturbance gets smoothed out immediately. The best way to picture it is to think of slowly pouring very thick honey. The flow is predictable, it's orderly, and it just follows this beautiful smooth path. But then, you crank it up past 4000, and now, the bully, inertia, is running the show. The fluid's forward momentum just completely overpowers its own stickiness. The slightest little disturbance, and the whole thing just erupts into those swirling eddies we talked about. This is a whitewater river, a plume of smoke from a chimney, or the water just blasting out of a fire hose.
So what about that middle zone, that transitional area? Well, it's just a mess. It's too unpredictable. The flow can literally flicker back and forth between being smooth and being chaotic. And look, in our field, predictability means safety. It means reliability. So this is a zone you design your system to stay out of it, period.
Okay, so enough with the theory for a second. Let's talk about the real world. Why does any of this matter on the job? Because for you, as a chemical tech or an engineer, this number isn't just an idea. It's a tool you are going to use every single day. I mean, you're going to use it for pretty much everything.
Trying to figure out what size pipe to use and how big of a pump you need the Reynolds number to calculate how much friction you're going to lose. Designing a heat exchanger? You absolutely need Re for that. Making sure a reactor is perfectly mixed? Yep, need it there too. And this last one? Scale up. This is where it feels like pure magic.
All right, so let me throw a question at you. Usually we think chaos and turbulence are bad things, right? Things we want to avoid. So why in the world would an engineer purposely create a chaotic, turbulent flow inside something like a heat exchanger? What's the benefit?
The answer is just a perfect example of why this number is so powerful. That chaotic flow is basically like a tiny microscopic scrub brush. It scours the inside walls of the pipe, and it rips apart this tiny insulating layer of slow-moving fluid that clings to the wall. And by doing that, your heat transfer goes through the roof. It makes the whole piece of equipment so much more efficient. You're literally weaponizing chaos to get the job done.
And it's the exact same idea in a reactor. A high Reynolds number is your guarantee that you're getting that perfect mix you need. And for scale-up, this is incredible. You can build a tiny, cheap model in the lab, and as long as you match the Reynolds number, you can know exactly how the full-scale, multi-million-dollar plant is going to behave. It saves an unbelievable amount of money and time in R&D.
Okay, so let's wrap this up. Let's talk about the payoff. Because understanding this one number, it's not just about passing a test. It's about efficiency, it's about safety, and it's about innovation in the real world. When you master this, the benefits are massive. You save a ton of money on energy because you can size your pumps perfectly. You get the most out of your processes by maximizing your reaction and heat transfer rates. You save millions of dollars by testing small models instead of full-scale plants. And most important of all, you make sure your plant is safe and it's going to run reliably day in and day out. But if you get it wrong, the consequences can be absolutely catastrophic. Miscalculate Re, and you get those unmixed hotspots in a reactor, and that can lead to a thermal runaway, to an explosion. In the biomedical world, bad flow design in an artificial heart valve can create turbulence so violent it physically shreds red blood cells. No joke. It's even part of why massive structures fail, like the infamous Tacoma Narrows Bridge that got torn apart by turbulent wind. So here's the bottom line. The Reynolds number is absolutely everywhere. So the next time you go to a sink and turn on the water, watch it. Watch how it goes from that smooth, clear, glassy stream to a gushing, white, chaotic mess as you open the tap further. You're not just looking at water anymore. You are watching that live battle between the bully and the peacemaker. And the cool part is, now you know who's winning.